Hello, my name is Howard Williams. I'm the Business Development Manager for Bray Automation and Controls. And today I'd like to show you the Bray S98 Electro-Hydraulic actuator. So we'll begin by talking about the actuator itself, and then we will refer it to the hydraulic power unit that we use to drive this actuator. This particular demo is mounted onto a triple offset butterfly valve, but obviously the actuator can be mounted on any type of rotary valve. The S98 Scotch Oak actuator consists of 2 or 3 main modules. The first module is the torque module, and this is the device that holds the Scotch yoke itself. The second module is the pressure module, and with this range of actuators we can do a low pressure pneumatic, or in this case, we have a high-pressure hydraulic pressure module. So this module is capable of being pressurized up to 3,000 psi. The third module on the far side of the unit, which is optional, is a spring return. So we can configure this actuator by using a various combinations of torque module, pressure module, and spring for a full range of torque sizes for all of the valve sizes. We can make it a double acting, where we're just using hydraulic pressure to stroke the valve in fully open and fully closed position, or we can add the spring module so we control the valve in one direction using hydraulic pressure, and when we release that pressure, the spring takes over and it strokes the actuator in the reverse direction. So as I mentioned, the pressure module can handle up to 3,000 psi. With an electro-hydraulic actuator, what we are talking about is a product that has the ability to create that hydraulic pressure on board of the actuator. So no accessories outside of what you see on the actuator is needed to operate the valve other than an electric power supply to the motor. On the Bray design S98, when we pressurize the pressure module with a spring return unit, we are pressurizing the inboard side of the module. And so we are pushing the piston in this direction away from the center body. And at the same time, the rod in the spring can is compressing the spring towards the center body. So that would be a normal power stroke. And then when we release this pressure, the spring will act outwards and it will pull the piston back to the inboard side. The other device that's mounted directly onto the actuator is this switch box we have. This is a Bray Series 5 switch box. This box can come with a number of different options for limit switches, either a mechanical, single pole, double throw switches, or various sensors. When we use it with an electro-hydraulic actuator, we typically, as standard, put in 4 single pole, double throw mechanical switches. Now, 2 of those switches will be used to operate and control the hydraulic pump, which we will talk about in a minute. But the other 2 will be available for customer use for end of travel indication in a remote control room. The other feature to point out on the torque module is the end of travel limit stops. So when we are setting the actuator on the valve and we're precisely positioning the valve to fully close, fully open position, we can control the movement of the yoke by either screwing in or pulling out these mechanical end stops. The other surface you see on the front of the module here, this is a mounting surface for adding controls. We mount these on both sides of the torque module, as well as we have a mounting configuration on the top, which is a Namor standard, which we can use to mount the limit switches or whatever other devices. On this particular actuator, we are using this mounting surface on the back side of the unit to put the hydraulic power unit, which we will explain about next. So now we're going to take a closer look at the hydraulic power unit, which is mounted on the side of the actuator. And that also breaks down into several pieces. First of all, we have a motor, which is driving the hydraulic pump. The hydraulic pump is actually submerged in this hydraulic oil reservoir at the bottom of the assembly here. And then the piece in between, this is a hydraulic manifold, which is machined to deliver the hydraulic fluid from the pump to the cylinder and then return back to the reservoir. The manifold is machined with many different ports, so we can use a manifold for many different configurations. So you'll see a number of plugs and so on around the edge of this manifold. The control of the actuator requires turning the pump on and activating a solenoid valve on the side of the manifold. So right now, the valve is in the fully closed position. In order to open it, we would have to turn the actuator on. So now we're providing electrical supply to the motor. And again, that motor can be an AC motor, a three-phase or a single-phase, or it can be a DC motor. So we're providing power to the actuator, and we're also sending a control signal to a solenoid valve. And those two functions will operate from this one switch. And you hear the pump come on, and the actuator opens the valve. Now, at the end of travel, the limit switch in this limit switch box on top of the actuator will send a signal to the controller inside the control box. The pump will then operate for a few more seconds to make sure that the maximum pressure is in the pressure module. Once that pressure is up to full, the unit will shut off, and it will remain in the fully open position because the solenoid valve here is holding the hydraulic pressure in the cylinder. To close this unit, because this is a fail-safe spring return unit, when we apply a closed signal, you'll see a very fast motion of the valve. And what that is that as soon as the control voltage is removed from this solenoid valve, it releases the pressure of the oil from the pressure module back into the reservoir. And so the spring, as you can see from the demonstration, is very powerful, so it can move very fast, okay? We can control the speed of that spring operation. So if you have a valve where you don't want to slam it into the seat, or you want it to close over a number of seconds, we have needle valves on the manifold that allows you to control that reverse flow of fluid going back into the reservoir. The control box here is where all of the electrical controls are based. This is a demo unit, so it has more buttons and lights on it than maybe a production unit would have, and we're going to talk about some of the functionality. But basically, if we just look inside the box here, you can see that all of the componentry in here is standard product. So when you look at a hydraulic actuator, electro-hydraulic actuator, there are many designs out there on the market. Our philosophy is we build the hydraulic power unit with standardized hydraulic components, which allows the end user to easily maintain and repair in the field. Same goes for the electrical components. We have a mini PLC in here which controls the flow of the hydraulic fluid. We have, as you can see, terminal blocks and switches and so on, which are on the front cover of the switch box here. These are all items that can be bought locally and serviced easily in the field without any special parts required. The local controls on the cabinet is optional. Many customers just want to control the actuator from the control room, so they won't necessarily have an open-close button on the front, nor will they necessarily have the red and green lights that we have on this particular demo. Usually, if it's in a remote location, any kind of local controls will need to be padlocked, so nobody can walk up to the actuator and operate it without the control room knowing about it. So whenever the local remote selector switch is set into remote, These buttons and lamps are disabled, and we're only controlling from the control room. Whenever you put this into local, then you can operate using the local switches, and the control room cannot control the unit. Typically, the local remote selector switch is also a feedback to the control room. So the control room always knows when there's someone on site and someone's put the actuator into local. They are always aware that that is a situation, and at that point in time, they cannot remotely control the actuator. So that's a safety feature. So typically, when you have a fail-safe spring return actuator, one of the decisions that has to be made is what causes the actuator to go into fail mode, okay? And that can be one of a couple of things. We could have a loss of the control signal that's holding the solenoid valve open, or we could have a loss of the electrical supply going to the motor, or in quite often the case, either or, okay? So normally what it means is the ability to be able to control the valve has been lost remotely, or there's some kind of other instrumentation associated with the flow in the pipe, which is sending some kind of emergency shutdown signal to the actuator. And again, the controls inside this box are customizable. So we typically work with the engineers who are specifying the product at the beginning of the process to determine what control logic they would like to see inside this box. If you have a situation where the power has gone out and the operators are in the field and they need to open the valve and the valve is in the closed position, we do have an option for that, and that is a manual override through a hydraulic pump. So on the same manifold block, on the back corner here, we have a manual pump. Now, if I remove the handle from its storage position and put it into the hand wheel here and pump it down, I'm actually not causing any pressure whatsoever, because in normal operation, that hydraulic pump is not in the live circuit. However, if I open this little gate here, and again, padlocked for remote locations, so you would normally have this so it wasn't accessible unless it was a certified operator. If I open up this little door, I now have a needle valve, and if I screw this needle valve in, the needle valve is in series with the solenoid valve, so I've effectively manually done the same as applying power to this solenoid valve. Now when I pump this, I got some pressure behind it, and you can see from the valve blade below, or you can read from the beacon indicator on the top of the limit switch box that I'm now moving the valve into the open direction. Okay, so that's a standard feature on all of the EH actuators. So put that back into storage mode, and at this moment in time, if I started the unit up again, we wouldn't get full operation because that needle valve is still closed in. So when I remove the needle valve, open the needle valve, you'll see that the valve is now going back to its fully closed position. So in normal mode, that needle valve is always wound all the way out, and we're only relying on the solenoid for normal electrical operation. The big advantage of the Bray S98 electro-hydraulic actuator is it's infinitely customizable. So the controls can be on-off for electric fail-safe. They can be 4 to 20 milliamp or network controls for modulating applications. And the components that we use in the build can also be specifically selected for certain applications. When we talk about safety valves, they are typically in very remote locations, and they typically don't operate very often. So this would be what we call line break service, where there are pressure sensors along the transmission line, and if there is a notable drop in pressure due to a leak or possibly a breach in the pipe, The control room wants to send a signal to the actuators on the valves on either side of the leak and shut in the pipeline to ensure that they minimize the loss of fuel gas. Because those valves are 99% of their life in the fully open position, there are federal guidelines mandating that the valves should be regularly exercised to make sure that when the ESD event does occur, the actuator is capable of closing the valve. So a ball valve, trunnion mount ball valve in a pipeline application is being open for a long period of time, there's a possibility the valve can get stuck. And therefore, is there enough energy in the actuator when the ESD signal is sent to close that valve? So in order to not completely shut out the pipeline flow, there is a function called partial stroke testing. And what that involves is just moving the valve, say 10%, just to confirm that the actuator is capable of getting it moving and that the actuator moves a proportion of the stroke in the normal operating time. That will tell the control room and the pipeline operators that the actuator is still functioning correctly and the valve is not stuck in any way. The way that partial stroke testing is done today is normally remotely using a control signal coming from the control room. So discrete partial stroke test will, the signal will be sent to the PLC inside the controller, and we will use a discrete partial stroke testing solenoid, and we will also be using a discrete limit switch in the limit switch box to determine the movement, the confirmation that we've reached the set movement, and also the PLC is measuring the time it takes to make that movement. So once a partial stroke test has been confirmed as complete, the PLC then sends a partial stroke success signal back to the control room. So on this demo, we've actually have a partial stroke button. Normally, as I say, this would just be a control signal coming in remotely. But in some cases, the customer still wants to be on site. The field technician wants to be on site and wants to physically witness the test. So a button can be provided in order to do that. So if I put the valve into the fully open position, and there we have our green lamp on indicating that the valve is fully open. And that lamp is coming from a limit switch in the limit switch housing. If I press the partial stroke button, you will see the valve move about 10%, and then it will stop, okay? At the same time, too, the orange partial stroke lamp comes on, and the red and green lamps are on, indicating it's in mid-travel. Once it's determined that it has moved that 10% and within the parameters of normal operating time, the PLC will then fully open the valve back up again. And the normal open light is now back on, the partial stroke lamp is off, and in the case of a remote control, the signal will have been sent back to the control room confirming that the partial stroke has been completed. That is just one of the special features that we can add into these actuators. Typically, when we're working with an engineer designing a new project, we like to build a data sheet determining exactly what parameters are required in the control philosophy, so we can come up with a schematic that meets the requirements of the application. Again, we've talked a lot today about on-off valves, fail-safe. If it's a modulating actuator where it's on a control valve and we're positioning with say a 4 to 20 milliamp signal from fully open to fully closed, similar concept, but we're using slightly different components. we're using, for example, a variable frequency drive motor. So when the actuator is moving to the set point, it varies in speed, and as it gets closer to the new set point, it slows down to avoid overshoot. And there's some other factors built into the whole design of the hydraulic system to account for the duty cycle. Typically, control valves are moving a lot as opposed to an on-off valve that opens and closes infrequently. So all of that is taken into account when we fill out the data sheet. We're interested in learning a little bit about the application and how often the actuator is going to be moving the valve, and on the basis of that, we will size everything accordingly. So that concludes the first look of the Bray S98 EH actuator. If you would like to see a demo like the one we have here, we do have traveling demos which we can bring to your office or site to present. We also have a lot of information, technical information on our webpage, or you can reach out to the local Bray sales office, and let's see if we can provide you a suitable product for your application. Thank you very much.